We're talking about Frappé. It's a tool designed for querying and visualizing large code bases in the millions to tens of millions of lines of code. And today I'll wish to be focusing mostly on the querying side of that. All right. Okay, I'll stick with that one then maybe. So this is just to say that this work is research. Oracle obviously doesn't commit to produce any of this, make it available. And any views that I express during the presentation are my own and don't necessarily reflect those of Oracle. So if we talk about understanding the behavior of really large code bases, the truth of the matter is in the source code, right? But for the type of software that I'm talking about, things like the Oracle database, the Solaris operating system, the JDK, these code bases are incredibly complex. It's systems level code. They often involve multiple programming languages, so things like C++, Java, PL SQL, and sometimes more. And they're also really, really big, so millions to tens of millions of lines of code. So trying to glean information from these really large code bases using just the raw text is obviously quite difficult. So with Frappé, we try and give users a better way of sort of accessing this information by modeling the software as a property graph. So we're doing this because we feel that graph is a fairly natural model to use in the software domain. We're already used to talking about things like call graphs, type hierarchies, directory structures, control and data flow graphs, and so on. And the graph model enables us to really easily overlay or cross-reference data from different information spaces. So when we're talking about software, right, we have information from the file system, or how the software is actually organized on disk. We have information from the build, so what files get compiled into what object files get linked into what executables, and so on. And then also from things like the preprocessor, so files including other files, expanding macros, and so on, before you get to the actual compilation phase. And of course, there's also cross-language calls that you sort of have to work out in terms of dependencies. But the idea is that if we have this graph model, we can then let users specify queries they have about the code in terms of this model. So just very briefly how it works. We provide compiler wrapper scripts. So from the source code, when they usually build their software, we provide drop-in replacements for the regular compilation tools. And that lets us keep track of all the dependency information of what gets linked together. And as well as, because we're wrapping them, as well as running the native compilation tools, we also run a modified version of the Clang compiler that we have a plugin in to access extra information about what's going on during the compilation. We then output information for each object file and read all that into a graph database. So at the moment we're using Neo4j, and we have that hosted on a server. So before I continue, I just wanted to give you a better idea about what this graph actually looks like in terms of software. So here's an incredibly simple program. But if you're familiar with C or similar programming languages, you can sort of hopefully see a little bit of what's going on. So we have nodes here that represent our executables or object files. And they have edges saying what other files that are also nodes they're compiled from, or what object files they're linked from. We then have sort of, from the files, we have the preprocessor relationships of includes and expansion edges to other files and macro definitions, as well as file containment edges to all of the symbol definitions that actually occur inside those files. And then information from the ST as well. So we have calls from call sites to definitions, as well as the local variables and so on inside of them. And so the nodes and edges are all typed here. So once this is available on the server, we then have a range of interfaces that users can use to query this graph. So we have plugins in the editors that they usually use. For the large C++ code bases that we deal with, this is usually Vim or Emacs. And then we also have command line scripts and a web-based interface for running these queries. So the use cases that we're targeting here are primarily code search and code navigation, more for the editors here. So things like jumping to a definition, finding references, but also more complex queries. So we do a bunch of visualization work where we try and use the information in the dependency graph to show an overall overview of the entire code base and its structure and how it's organized. And then we also do things like transitive closures of edges. So for example, if I'm looking at a particular header file, I might want to know all of the C files that is transitively compiled into. And then also shortest path queries. So it's really useful for a developer to know that, okay, from my entry point, whether that's an API point or a main method, how does execution reach my particular function via a sequence of calls edges? So in terms of how that looks, for code navigation, how you'd imagine, so if I put my cursor over a particular symbol, I can do a key combination and see all the references corresponding to the incoming edges in our graph here, down the bottom. In the web UI, they can do a search for a particular symbol, see the corresponding source code, and that's all cross-referenced using the information, the source code information we have on the nodes and edges as properties. And then in the web UI, we have this visualization of the code showing the directory structure and files here. And then for the red here is a particular function. We're looking at the transitive closure of calls from that function. So this is basically all the functions that could potentially be executed from my particular function of interest, as well as a shortest path query from one function to another. So how can execution get from point A to point B? So in terms of these use cases, we presented most of these at Grades in 2015 with sample queries of how we're implementing those as Cypher queries. And for most of them, performance is fairly well, but any query that has a transitive closure in it, so for example, some node n that's a function has a calls star relationship to something else, generally the performance falls over with the size of the graphs that we're dealing with. And all we want out of that is really this reachability rather than actually keeping track of the paths themselves. And some of the simpler queries actually have these transitive closures embedded in them. So something like code search you might think is quite simple. So if I type foo.c, how do I find the nodes that match that? Well, we just look for nodes that have this name, foo.c. But dot is also field access in C. So what I might actually be looking for is some struct called foo that contains the field C. So my query needs to be a little bit more complex, right? I want some way of grabbing some container with the name foo that has a contains edge to my field of name C. So we're done, right? But there's also these things called type defs in C. So maybe foo isn't a struct. It's actually a type def. This is basically an alias. So foo here is an alias to this struct which contains C. So I need to add this transitive closure here of aliases edges, because you can have a type def of a type def to then return the match that they're actually looking for. And going even further, if you have some C++, maybe foo is a base class somewhere. So foo is a derived class that doesn't actually implement the method C, but it inherits from some class further down the chain that does. So that's even more complicated still, because you need to check visibility properties as you go. I just want to emphasize that reachability queries are really important in this domain. But what we'd also like to do, obviously, is expose, in all of our UIs at the moment, we only provide either key combinations or buttons or features in the UI that run canned queries. And for a lot of these code bases that we're talking about, they have very specific use cases. They might have certain constraints that they want to enforce on their architecture, and they have no way of really doing that at the moment. So we really want to be able to expose this query language for this type of anti-pattern detection. And there's a few issues of expressiveness that sort of prevent us or make us reluctant to do that with Cypher, for example. So if I wanted to do something like a dependency cycle, so this is a case where we have a circle of dependencies, which you generally don't want to see in a program. So say we have 3 source files here, and we want to detect cases where there's a cycle between 3 files, for example. So we have one source file that contains some node that references some other node that's contained in another file. And that pattern repeats between these 3 files to form this circular dependence. So what we really want is the equivalent of the star kind of syntax, but for a sequence of edges. So in this case, this is the sequence that we want to repeat between our 3 nodes here. Of this file contains reference, and then incoming file contains. And there's, not that I'm aware of, there's no way to express that currently with Cypher. But it's also there's some other things that you could express. So this references edge down the bottom here, we don't actually have that in our graph, right? All of our edge types are quite specific, because we want users to be able to select just the subsets of edges that they're interested in if they want to. So we have quite a few of these. So if I wanted to capture this idea of all the references between these two functions, that actually corresponds to quite a few edge types. So if the user is having to enter these queries, they then sort of have to iterate through all of these. So it would be really useful if we had some way of sort of abstracting into sort of categories of edges that we wanted to match. So they don't have to keep sort of typing these out or copy pasting if they're repeating it, for example. Or just having multiple labels per edge or some other feature that gets around having to do that. But the other thing, so all of this stuff that I've talked about so far is just sort of looking at one snapshot of the code. To make this work in practice, not all the developers are working on this one magic version of the code. They're usually like a version from a few days ago that they've made changes to, or on some other branch or something like that. So to make this thing useful in practice, we really need to not look at just a single version, but ideally this multi-version reality. So what we're really aiming for, the scenario that we're in, is that we have thousands of developers working off this main branch. Changes are usually merged back quite regularly, so often they won't be further than maybe versions from 30 days ago or so. So you can handle the majority of users if you have just these more recent versions. But in our current deployment, we're actually running a separate Neo4j instance for the most recent 5 versions, which is what fits on our server that we're using at the moment. And then basically, as part of the nightly regressions, we'll generate the data for the new version, make that available and drop off the oldest. So it's on a rotation there. And then on their client machines, we just got a little script that points them at the version available that most closely matches the version that they have. Yeah, so I mean, obviously that's not ideal. There's a deployment effort and complexity. I mean, we actually have 5 different servers. When we could, obviously, it's better if we encapsulate that in one logical server in terms of deployment. But it's also a fairly inefficient use of resources. So these giant code bases from one day to the next are mostly the same. Like the amount of change from one version to the next is not very much. So ideally, we'd have some way of deduplicating that data and storing it efficiently across multiple versions. So it's really a fairly inefficient use of resources because the redundant data occupies memory and also disk. So we're really wanting to move this to this model where we have a single logical server supporting multiple versions and an efficient storage mechanism. So I mean, in terms of use cases for multiple versions, the first one is obviously that, OK, we want to do all the things that we could do for the single version, but on the version that the user is actually using. So if you look about something like that in terms of the querying, obviously we could do this duplication in our graph model, but then the user has to become aware of the model we're using to how we're modeling these versions to write their query, which obviously makes it a lot more simpler. Whereas if the database, or at least the query language, can abstract that versioning away, they can just express the more simpler version of that query that they're actually after. But I mean, if we have multiple versions, there's also a range of other use cases you can fulfill. So if you have 2 versions or you're making a change, generally what you're more interested in is a comparison between versions. So if I had some pattern that detected some architectural constraint being violated, what I'd be more interested in is seeing the new violations in after my change compared to before it, or to enforce these kind of things in practice. So, or similarly, like, are there any new usages in this change of any deprecated methods or things like that? That one's a fairly trivial pattern match. But in each of these cases, the query, you never actually have any queries that are matching paths across versions, right? It's always a match in version A, a match in version B, and being able to compare those results. So just in terms of querying, if we had this magic version syntax, you can imagine if we wanted to find all the new paths or something like that between some source function and some sync function, we can do our query at the top and difference that with our query with the different versions selected. But in fact, for a lot of those types of queries, it's the same pattern match that you want to do on both versions. So it'd be cool if there was some sort of syntactic sugar to abstract that away too. So I mean, I don't expect anyone to actually follow these syntax, but just so you don't have to keep repeating that pattern, because some of them get quite complex. So I mean, obviously, the thing I'm not talking about here is there's a very open issue of like, how do we node edge identity? So I mean, the user can supply these IDs, in our case us, Or perhaps like there'd be some way of deciding based on certain properties what made one node in the old version be the same node in the new version. But I think for software that's actually quite complex, so not necessarily the problem of the database. So also just mentioning a few things about query language expressiveness. So this idea of regular path expressions, like having some way of having different edges in different directions and types in sequence is really important. And also multiple edge labels is convenient because in this domain at least we have a lot of different edge types. So being able to work with them in sort of sets or like containments or references is quite useful for some of the queries you want to write. And finally, some efficient mechanism for storing and querying these multiple version graphs. So we'd settle for a list because that gets us a lot further than we are now. But ideally, in reality, there is a DAG of versions. And then, if we have these multiple versions, supporting a way of unioning, intersection, and difference of the results from the matches from different versions, and having that abstracted away in the query language would be ideal. So this is a really big wish list, really. But just to get a feel for some of the things in this domain that make sense. So we recently made available the FreeBSD kernel graph that Frappé is generating. And we've got versions that include graphs of the 10.1 kernel, the 10.2 kernel, and the 10.3 kernel, along with documentation on our graph model and edges. So each graph is extracted from a code base that's roughly 10 million lines of code. It increases from the older version to the newer one, and around 2 million edges or 2 million vertices and 10 million edges. And that's available on OTN. So if you go to oracle.com/technology-network, you can download these data sets if you want to try them out with your graph technology. And of course, feel free to get in touch with us. We're very interested in getting some of this stuff supported. And I'd also encourage you to view, I think the PGX guys are presenting some work that actually solves a few of these issues on Friday. So come along to that if you want to see how they're doing it. And yeah, that's all. Any questions?
So have you tried to use PGX?
Sorry, at the moment we're kind of starting to do that, but some of the path querying stuff they're still working on at the moment. Yep.
On the case where you've got the horrible or statement,
yes.
50 or
yeah.
bars, it strikes me that if we had a true concept of typing, if we could say that there was a base class.
Right, a hierarchy of types. Yeah.
Hierarchy.
Right.
It would be a more elegant way of handling this than just textually.
Yes, definitely.
Otherwise, you're just looking for syntactic sugar.
Right.
Yeah.
I was going to go through that. My first question was, what is the schema of this? Because you said, there has to be looks like there's some well-defined schema, which is a file located in references, but it seems that references has all these sub-properties in there.
Yes.
Reference can be that. So it seems that what you were talking, and even your wish list of having path expression stuff, that's all in RDF and Sparkle, and you can be able to represent this as some sort of a schema ontology with sub-properties and subclasses and do scene and be able to abstract this all the way, and you have named graphs and stuff. So I don't know if you looked into that, because it seems that you can do this all with RDF.
Yeah, like I guess we could evaluate RDF. Like to us, the property graph model seemed more natural for expressing some of these queries.
I would disagree.
Yeah?
But that's for later.
Okay. Yeah.
A bit more of on the code analyst question. How do you deal with function pointers?
So at the moment we don't. We have, if there's a function pointer in a local variable, we have a calls edge going to the local variable. Yeah. So one thing we were looking at doing is modeling value flows in our graph, so that we could potentially, for a particular pointer, say, okay, what can this potentially point to? It wouldn't be completely precise, but certainly a lot more precise than it goes nowhere. So we haven't done that because we're sort of dealing with graph scalability issues at the moment. I mean, if we do that, we have a lot more edges. Just for example, we don't have argument nodes at the moment. So just adding them obviously adds a lot extra nodes for every. Parameters is one of our most frequent node types. And if we add arguments, that multiplies that by every call site. So we're sort of keeping it simple for now and trying to see how we can make what we have useful. And in practice, and then we'll sort of start trying to be a little bit more fancy. Yeah.
But it looks like a really useful facility. I'm surprised that Larry hasn't asked you to ship it yet. It's a very interesting concept, though, isn't it? I mean, this is to be able to have this kind of analysis is very valuable, I would have thought.
Yeah, I definitely think. I think the domain in general, like applied to graphs, makes a lot of sense. Yeah. Yep.
Are you representing module interdependencies like shared libraries as well? DLLs or shared libraries using build information?
Right. So I think we won't pick that up at the moment. Like any source that we compile, we have information for. If we don't compile it, we don't know anything about it.
Okay, so you're not parsing the source itself. You're using a compiler add-on on top of like GNU or something, and then taking information.
So we're using the Clang compiler. We have a Clang plugin, and so if we compile the code, we know about it. But if we don't, if it's an existing shared library, we don't. Yeah.
I have another question.
Sure.
How are you keeping track of the architectural constraint violations?
So we're not. We're not exposing the query language at the moment, but we wanted to provide them a way to express some of those. So I mean, if you had for C code, they have to define their boundaries of like whatever's in this particular set of source files. Like whether a directory defines that, and we can follow down from the directory structure to the actual C files that contain references to other stuff, or whether it's certain object files, and however they choose to define it. If certain things aren't allowed to depend on certain other things, or you have like a encapsulation of something, and there's edges that go directly to some private, fields that are private in C. Being able to detect those really quickly is obviously useful. So it was more just a theoretical, because we want to give them a way to express these, because it is generally different per code base. Cool.